Padua, January 7, 1610. A 45-year-old mathematician climbs to his rooftop with a new instrument. His glass magnifies the sky 20 times. Tonight he aims it at Jupiter. The Aristotelian universe has 6 hours left. In the time it takes you to read this sentence, light from Jupiter has traveled about 43 million kilometers. That light carries an image of the planet as it looked 35 minutes ago. Every observation of the sky, ancient or modern, is an observation of the past. The night this man climbs to his rooftop, he does not know that number, but the light he is about to gather has already been traveling for 35 minutes before it meets his lens. His name is Galileo Galilei, born in Pisa on February 15, 1564. In January of 1610, he is 45 years old. He has held the chair of mathematics at the University of Padua since 1592. His annual salary is 520 florins, comfortable, not extraordinary. He has 3 children by Marina Gamba, a woman he has not married. His household is constantly short of money. He is respected inside the Venetian Republic. He is unknown beyond it. He is not yet the Galileo history will remember. He is a teacher of geometry and military fortification, occasionally a tutor to wealthy Venetian sons. He has published almost nothing. His best-known work is a short pamphlet on the use of a military compass. He lectures on the Ptolemaic system, as required. He has also read Copernicus. In private letters to Kepler in 1597, he admits that he finds the heliocentric argument persuasive. In public, he teaches Earth at the center. To do otherwise in a Paduan classroom in 1609 would end a career. The universe Galileo inhabits is Aristotelian. It has held largely unchanged for almost 2,000 years. Earth sits motionless at the center of everything. Around Earth turn 7 crystalline spheres, each carrying one of the classical planets. Beyond those, an 8th sphere carries the fixed stars. Beyond that, nothing or the prime mover, depending on the commentator. In this cosmos, everything above the sphere of the moon is perfect, unchanging, and eternal. Everything below the moon is mutable, corrupt, and subject to decay. The heavens are made of a 5th element, ether, which moves only in perfect circles. Consider the scale of that universe. The sphere of the moon turns closest to Earth, pressing against the upper air. Beyond it, Mercury, Venus, the Sun, Mars, Jupiter, Saturn. Beyond Saturn, one sphere of stars pinned like lamps to an inner dome. In this model, the whole cosmos is perhaps a few tens of thousands of Earth radii across. Your body is about 170 centimeters tall. Earth is about 12,700 kilometers across. In Galileo's inherited model, the stars sit only a few 100,000 kilometers beyond Saturn. Modern measurement places the nearest star system 4.2 light-years away, about 40 trillion kilometers. The universe Galileo was trained to teach was about 100 million times smaller than the real one. He does not know this yet, but the Aristotelian universe has been showing stress for a generation. In 1572, a new star had flared in Cassiopeia, brighter than Venus, visible for 16 months. Tycho Brahe had measured it and shown that it sat beyond the moon in the sphere that was supposed to be eternal and unchanging. In 1577, a comet had passed through regions Aristotle said no material object could enter. Kepler, in 1609, had just published his Astronomia Nova, proposing that planets move in ellipses, not circles. Galileo owns a copy. He has not yet worked through every argument. And now, in the late summer of 1609, a rumor reaches Venice. A Dutch lens grinder named Hans Lippershey has petitioned the States General for a patent on a device that makes distant objects appear close. Galileo hears the description in August. He does not see the instrument. He hears only that it works. Before this January night on the rooftop, Galileo writes a certain kind of prose. His surviving manuscripts from the 1590s, the unpublished D'Amato drafts, his Paduan lecture notes, his correspondence with the jurist Paolo Sarpi, average about 19 words per sentence. They lean on Latin subordinations, periodic constructions, abstract geometry. The subject of each sentence is usually a thing in general, a body, a motion, a proportion. Specific times and dates are rare. Specific observations are rarer. He is a reasoner, not yet a reporter. The stylometric baseline matters because in 4 months his prose will change. In March of 1610, he will publish a short book, Sidereus Nuncius, the Starry Messenger. Its sentences will average about 14 words. Its subjects will be specific. This planet, this moon, this night, this hour. Metaphor density will drop. Observational verbs will rise. You can date the cognitive shift almost to the week. It happens in early January of 1610 on a rooftop in Padua with an instrument that has just been built. The instrument is called a perspicillum, Latin for a device to see through. Galileo builds his first one in late August or early September of 1609, working from a description alone. He has never examined a Dutch example. He understands lenses well enough to reconstruct the principle. A refracting telescope at its simplest is two lenses in a tube. The lens at the front, the objective, is plano-convex. It gathers incoming light from a distant object and brings that light to a focus behind the lens. The second lens, the eyepiece, sits near that focal point. In Galileo's design, the eyepiece is plano-concave. Concave lenses spread light. Placed just before the objective's focus, a concave eyepiece intercepts the converging cone of light and bends it back into parallel rays that enter the observer's eye as if the original object were much closer than it actually is. The magnification of such a telescope is the ratio of the focal lengths. Objective focal length divided by eyepiece focal length equals magnification. Galileo's first tube produces about 3 times magnification. A useful toy. He grinds new lenses. His second tube reaches 8 times. He brings that one to the Venetian Senate on August 21, 1609, and demonstrates it from the Campanile of San Marco. Senators pick out ships at sea 2 hours before the ships reach the harbor. The Senate doubles his Padua salary on the spot. 8 times is not enough. By late autumn, Galileo has ground enough pairs of lenses to reach approximately 20 times magnification. This is the instrument that changes everything. The tube is about 1.2 meters long. The objective is a disc of Venetian glass roughly 40 millimeters wide, figured plano-convex. The eyepiece is a smaller concave lens about 22 millimeters wide. Galileo grinds the lenses himself on a treadle-powered lathe in his house on the Via Vignali, in the parish of San Francesco. He grinds and polishes hundreds of lenses over 3 months. Most are optically useless. Venetian glass is full of bubbles and striations. Most pairs will not focus. The pair he mounts in December of 1609, carefully tested and set, performs better than any telescope then on Earth. Consider what this instrument can resolve. The unaided human eye resolves about 1 arc-minute. The smallest angle 2 points can separate and still be seen distinct. 1 arc-minute is 1/60th of a degree. A 20 times telescope brings that threshold down to about 3 arc-seconds. That is the width of a human hair seen from 100 meters away. Jupiter in January of 1610 spans about 45 arc-seconds across the sky. To the naked eye, it is a bright yellow point. Through a 20 times glass, it becomes a small, clear, measurable disk. Consider the scale this makes available. Your hand, held at arm's length, spans about 10 degrees of sky. The full moon spans about half a degree. Jupiter, at 45 arc-seconds, is 72 times narrower than the moon. Its 4 closest moons, when they reach greatest separation from Jupiter, sit within 10 arc-minutes of the planet, a region smaller than your fingernail at arm's length. Without magnification, they are fully invisible. The combined brightness of Jupiter's glare erases them. With 20 times, their glare ratio collapses. What had been 1 object for every pre-telescopic human astronomer, Babylonian, Greek, Chinese, Mayan, Islamic, European, becomes, briefly and for the first time, 5. Galileo begins using the 20 times perspicillum in late November or early December of 1609. His first sustained observations are of the moon. He draws its terminator, the line between its lit and dark halves, and notices that the lit side is not smooth. The shadows move across days. He concludes that the moon has mountains and craters. He measures the height of some mountains by the length of their shadows. He estimates peaks of several thousand feet. The result is the first step toward ending the doctrine of lunar perfection. It is also, for the historical record, a rehearsal. The 7th of January of 1610 is what is coming. The instrument is finished. The observer is 45 years old and has been sharpening his eye on the moon for a month. The sky is clear above Padua. Jupiter has risen above the horizon. It stands high in the east at its brightest of the winter. The mathematician sets the tube on a low wooden mount, a simple pivot. He sits in an unpadded chair. He places his eye at the lens. He waits. The first hour of the night following January 7th, 1610. Galileo's own phrasing, later in Sidereus Nuncius. Die septima Ianuarii instantes anni millesimi sexcentesimi decimi, Hora proxima sequenti noctem. On the 7th of the present year, 1610, at the first hour of the night that followed. He does not that evening expect revelation. He expects to refine his measurement of Jupiter's disk. In the field of his 20 times glass, Jupiter appears as a pale ochre circle, not a point as it appears to the unaided eye, a circle. He can see the circle's edge, and near that edge, on a straight line cutting across the planet's face, he sees 3 additional small lights. He records them. The 3 lights are very close to Jupiter. They are closer to the planet than any true fixed star should appear. Stars do not cluster like that, not in his atlas, not in any astronomer's catalog. They are also dimmer than Jupiter but brighter than the background sky. He draws their positions in his notebook. On folio 28 recto, he sketches Jupiter as a small circle with 2 dots to the east of it and 1 dot to the west. He labels them stelli fixi, fixed stars. That is what he thinks they are on the night of January 7th. Faint background stars, accidentally lined up, as stars sometimes seem to line up behind a planet. He closes the notebook. He goes inside. He writes a letter to the Tuscan court, nothing unusual. Right now, reading this, you are sitting where Galileo was sitting that night. A human being trying to understand something vastly larger than yourself, with nothing but a lens and a notebook, and the sky refusing to stop. You already know what he is about to find. He does not. That is the difference. Every recognition in the history of the sciences begins in that gap. On the next night, January 8th, Jupiter is still in the field. Galileo sets up his tube again. The sky is clear. He looks. The 3 small lights are still there, but their positions have changed. Now all 3 are to the east of Jupiter. The night before, 2 had been east and 1 had been west. Overnight, one of them has crossed the planet. He freezes. Stars do not cross planets in a night. Stars do not move across the sky relative to a planet on a 24-hour time scale. The Earth's rotation moves the whole sky together. The star patterns stay fixed. If the 3 small lights were truly fixed stars, Jupiter would drift past them over days and the stars would stay still. The pattern that has appeared is the opposite. Jupiter is holding position in the background star field. The 3 small lights are moving with it. He draws the new configuration. Folio 28 verso, 3 lights now all east. He writes a single word in the margin, Myra. Remarkable. That is the cognitive event, not the first observation on its own. The comparison of 2 nights held in a single mind, forced to admit something the inherited cosmos does not permit. Objects too small to see with the unaided eye, moving around another planet in periods of days. Consider what he has just recognized. Your body contains about 37 trillion cells. Each of those cells holds about 2 meters of DNA coiled into a nucleus 6 microns across. When you stand in sunlight, a photon that left the sun 8 minutes and 20 seconds ago passes through your body in less than a nanosecond. All of these are scales smaller than your skin. Above your skin, the distances scale the other way. Earth is 13,000 kilometers across. The Earth-Moon system is 384,000. The Earth-Sun system is 150 million. Jupiter sits at 5.2 astronomical units, 779 million kilometers from the Sun. The light second, the light minute, the light hour, the light year, each a step in a ladder your nervous system did not evolve to climb. The first rung Galileo climbs that week is small, 4 points orbiting a planet that is not Earth. The implication is enormous. Something in the sky moves around a center that is not the terrestrial center. The Aristotelian universe is incomplete. He continues observing. January 9th, cloudy, no record. January 10th, 2 small lights to the east. January 11th, 2 east, 1 west, but the west one is very close to Jupiter. January 12th, 3 east. January 13th, 4. 4 small lights now, not 3, arranged on a straight line across Jupiter's equator, their positions visibly shifting from night to night. He watches them for weeks. He records their angular separations. He begins to estimate their orbital periods. By the end of January, Galileo has determined that there are exactly 4 of them. He has started to map their motions. He has realized that they all orbit Jupiter, not Earth. He has also realized that he is the only human being alive who knows this. On the 30th of January, he writes to Belisario Vinta, the Tuscan Secretary of State. He describes his observations briefly and promises a book to follow. He names the 4 new bodies Sidera Medicea, the Medicean stars, in honor of the Grand Duke, Cosimo II. The naming is strategic. Galileo wants a position at the Medici court. He gets it. By July of 1610, he has left Padua. The cognitive event, what the historical record actually shows, is the straight, simple, measured recognition that Earth is not the only center of orbital motion. He writes it down, it will be printed, and the inherited universe will not recover. Sidereus Nuncius, the starry messenger, is printed in Venice on March 13th of 1610, less than 10 weeks after the first observation. The print run is 550 copies. The book is short, about 60 folio pages in plain Latin. It contains Galileo's lunar drawings, his star observations in Orion and the Pleiades, and the night-by-night record of the 4 Jovian bodies from January 7th through March 2nd. 6 Venetian printers worked on the sheets. The first copies sell out within days. Copies reach Prague within the month. Kepler has his on April 8th. Read the book alongside Galileo's earlier writing and the change is measurable. In his 1590s manuscripts, his average sentence runs about 19 words. In Sidereus Nuncius, the average is closer to 14. In his earlier work, sentence subjects are abstract, a body, a proportion, motion in general. In the new book, subjects are specific, this star, this night, this moon. Observational verbs, I saw, I observed, I drew, I measured, appear at roughly 3 times the density of the earlier work. Metaphor density drops. Geometric diagrams rise. Drake's biographical chronology of 1978 catalogues the change sentence by sentence. What had been a theoretician writing in periodic Latin is now a witness writing in plain, date-stamped description. The shift is not just rhetorical. The discipline it signals is the one modern science is built on: show the observation, show the date, show the measurement, let conclusions follow the evidence. In March of 1610, Galileo is perhaps the only working scientist in Europe doing this as a default. Within a century, it will be the standard. The reception of the book is rapid. Kepler reads it in early April and writes a pamphlet titled Dissertatio cum Nuncio Sidereo, Conversation with the Starry Messenger. Kepler has not yet looked through a telescope. He accepts Galileo's account on stylistic and mathematical grounds. He writes that the 4 new bodies confirm the harmonic system of the heavens he has been deriving. In May, in Germany, the astronomer Simon Marius claims he had observed the moons independently in December of 1609. Marius's claim is disputed. The 4 moons will keep the names he suggests: Io, Europa, Ganymede, Callisto, but priority of publication is credited to Galileo. In June of 1610, Galileo negotiates a position as chief mathematician and philosopher to the Grand Duke of Tuscany. He leaves Padua in July. He moves to Florence. His annual salary rises from 520 florins to 1,000 florins. He is given accommodations, freedom from teaching duties, and a court title. He is 46 years old. His private life remains complicated. He places his 2 daughters in a convent near Florence at Arcetri, where they take the names Maria Celeste and Arcangela. Only his son, Vincenzio, remains in his household. Over the next year, he turns the instrument on other objects. He observes the phases of Venus in late 1610, a crescent, then a gibbous Venus, evidence that Venus orbits the sun rather than the Earth. He observes sunspots in 1611, then in 1612, and publishes the letters on sunspots in 1613. He resolves the nebulous bands of the Milky Way into individual stars. By 1615, he has begun to speak publicly in favor of heliocentrism. In 1616, the Inquisition issues its first injunction against teaching the Copernican system as physically true. In 1632, at the age of 68, Galileo publishes the dialogue concerning the 2 chief world systems. In 1633, he is tried in Rome and sentenced to house arrest. He remains under arrest for the last 8 years of his life. He dies on January 8, 1642, in the villa at Arcetri. He is 77 years old. Place that lifetime on the cosmic calendar. The universe, by current measurement, is about 13.8 billion years old. Galileo lived for 77 of those years. 77 divided by 13.8 billion is roughly 5.6 parts in 1 billion. In percentage terms, Galileo's entire life occupied 0.0000056% of the universe's age. Every observation he made, every lens he ground, every night he climbed to his rooftop, all of it happened inside a flicker. And yet inside that flicker, the inherited picture of the cosmos was rewritten. The cognitive signature persists into the last letters. In the years of house arrest at Arcetri, old and blind in the last 4 years, Galileo dictates correspondence to his student Vincenzo Viviani. The sentences are still short. The vocabulary is still observational. The style that began on the rooftop in Padua holds for 32 more years. In early January of 1642, on roughly the anniversary of the first observation, he dies within view of the sky he can no longer see. Viviani records those last days in careful, specific, date-stamped prose. The voice of the notebook is the voice the world has inherited. What Galileo saw, he understood through the tools of his era, 4 bright points on a line, orbiting a planet other than Earth, dismantling the geocentric cosmos one night at a time. What we now see, through 4 centuries of instruments and 5 decades of spacecraft, is something he could not have measured. Io, the innermost moon, is the most geologically active body in the solar system. It has more than 400 confirmed active volcanoes. The Voyager 1 spacecraft discovered the first of them in March of 1979, a plume rising over 200 kilometers above the moon's surface. The Galileo spacecraft, orbiting Jupiter from December 8, 1995 through September 21, 2003, mapped ongoing eruptions. The Juno spacecraft, in orbit since July of 2016, continues to image Io's volcanic plumes. The energy for this activity does not come from internal decay, as on Earth. It comes from tidal flexing. Io, Europa, and Ganymede are locked in a 1-2-4 orbital resonance. The Laplace resonance, first described mathematically by Pierre-Simon Laplace in 1798. The tidal stretching heats Io's interior. Its surface temperature runs near -160 Celsius. Its volcanic vents can exceed 1500 degrees Celsius. It is the hottest and coldest body Galileo ever saw, on the same night, through the same lens. Europa, the second moon, holds beneath a 15 to 25 kilometer ice shell, a subsurface liquid water ocean between 60 and 150 kilometers deep. By current estimates, that ocean contains roughly twice the water volume of all Earth's surface oceans combined. The NASA Europa Clipper spacecraft, launched from Kennedy Space Center on October 14, 2024, is expected to arrive at the Jupiter system in 2030. It will perform 49 close flybys of Europa. Its Europa UVS ultraviolet spectrograph is designed to detect water vapor plumes over the ice. Ganymede, the third moon and the largest moon in the solar system, is larger than the planet Mercury. Its diameter is 5,268 kilometers. It possesses its own internally generated magnetic field, the only moon in the solar system known to have one. The Galileo spacecraft's magnetometer confirmed the field in 1996. A liquid iron core drives it. The European Space Agency's Jupiter Icy Moons Explorer, JUICE, launched from Kourou on April 14, 2023. It is scheduled to enter orbit around Ganymede in December of 2034. It will be the first spacecraft to orbit a moon other than Earth's. Callisto, the outermost moon, carries the oldest unchanged surface in the solar system. Its density of impact craters is higher than anywhere else measured. The surface has not been geologically reset in over 4 billion years. It is, in a sense, a frozen photograph of what the inner solar system endured during the late heavy bombardment. Galileo saw 4 points of light. We now see 4 geological worlds, one volcanic, one ocean-bearing, one magnetized, one ancient. Galileo's recognition across 2 January nights in Padua has a specific structure. A single observer, a single instrument, a comparison between 2 moments in time, a conclusion the inherited picture did not permit. That structure, observe, record, compare, infer, is the working kernel of every modern science. It travels from a rooftop in Padua to the control rooms of Cape Canaveral to the magnetometer readouts of Juno. What Galileo saw was 4 bodies orbiting a planet that was not Earth. What we now see on Europa alone is an ocean twice the volume of Earth's surface oceans beneath a shell of ice. What we do not know, and cannot yet know, is whether anything is swimming in that ocean. We are building spacecraft to find out. The answer may arrive in our lifetimes. It may not. The question is one Galileo set in motion with a single comparison between 2 nights of observation, and it remains open. On this channel, we reconstruct the moments that ended the human size of the universe. Next week, Caroline Herschel, the Hanoverian singer-turned-astronomer, the first woman paid to sweep the sky, and the night in August of 1786 when she found her first comet alone through a 5-foot reflector, and began the 50-year diary of observation that would outlast her brother, her hearing, and the century. Description: a clinically precise minute-by-minute reconstruction of January 7-8, 1610. The 2 nights Galileo Galilei pointed his custom 20 times magnification telescope at Jupiter and effectively dismantled the Aristotelian universe. Stripping away the mythology, the script traces the profound cognitive and stylometric shift that birthed the modern scientific method. Before leaping forward to connect his 4 pale points of light with modern Voyager, Galileo, Juno, and Europa Clipper data.